Chapter 8 continues on with probability, but talks about two specific settings and the calculations associated with them, opposed to the variety of probability situations we looked at in Chapter 6. These two specific distributions are called binomial and geometric distributions. We'll spend quite a bit of time talking about the binomial case, and if you have a good handle on that, the geometric distribution should be pretty easy to pick up. In order for us to use the binomial calculations that we will discuss in this chapter, 4 things need to be true. So we call this the binomial setting. First and foremost, each observation is going to fall into just one of 2 categories, for which we're going to call success or failure. An example of this might be you draw a jack or you do not draw a jack from a deck of cards. We don't want to talk about multiple scenarios at once. Second, there's going to be a fixed number of observations. We use the letter N to represent the number of trials that we are going to have. The N observations, or again the N trials, are all independent from one another. So knowing the result of one observation tells you nothing about the others. We've talked about this independence piece quite a bit. Then the probability of success, which we're going to call P, is the same for each observation, and that's tied to the independence piece as well. So just to recap, we have 2 categories, success or failure. We have a fixed number N observations. The observations need to be independent from one another, and the probability of success is the same for each observation. Now, if the data are produced in a binomial setting, again, it qualifies for all of these 4 pieces, then the random variable is x, so we're still using the concepts from Chapter 7, or the notation anyway, x equal to the number of successes. And then the probability distribution is called a binomial distribution. Just as we have shorthand notation for normal distributions with a given mean and standard deviation, we have a similar notation that we might use for the binomial setting. So anytime you see in front of the parentheses B, we know that we're in the binomial case, and then the first letter in there, N, is going to be the number of observations or number of trials. So just as was listed above, and then P, again, is the probability of success. If you haven't had a moment to do so, please read examples 8.1 and 8.2 in your textbook. They should be on page 514. And we want to know the big difference between them. So what makes 8.1 a binomial setting, but 8.2 not a binomial setting? You should conclude upon reading these examples that in 8.2, independence is violated because we are pulling cards from a deck without replacing them, whereas in 8.1, not only is independence satisfied, but the other 3 conditions are as well. So it's important that you understand any violation of the 4 characteristics deems a situation not to have a binomial distribution. And if this is the case, then we won't be able to use these calculations that we will go through in just a moment. Another piece we want to consider is that when the population is much larger than the sample, a count of successes in a simple random sample of size n has approximately the binomial distribution equal to the sample size P and the proportion of successes in the population. I'm going to go through example 3 to help you understand what that sentence means. So on page 515 of your book, we have an engineer who's choosing a simple random sample of 10 switches from a shipment of 10,000 switches. Suppose that 10% of the switches in the shipment are bad. The engineer counts the number X of bad switches in the sample. So in this case, our success is finding a bad switch. So remember, success isn't always favorable. This is not quite a binomial setting because he's going to be removing one switch at a time, and when he does so, just as we remove a card from a deck, we are changing the pool from which we are pulling from. However, because the pool is so large, because we're talking about 10,000 switches here, when we then, when we remove one and go back in and have 9,999, even though the probability changes, it changes very, very little. So even though it's not quite binomial, because of the large sample size, or the large population rather, we are able to use the calculations as an approximation to answer this question. We'll talk eventually about how large is large enough. I'd like you to next practice looking through some scenarios trying to determine whether or not the binomial distribution has been satisfied. You should try problem 8.1 and see that the answer is no, but I don't want you to just write down no. I want you to explain specifically what condition or conditions are violated. For 8.3, yes, this is a binomial setting, and for 4 and 5, they are not either. So just as you did for number 1, I'd like you to identify which pieces have been violated. Example 8.5 on page 517 talks about inheriting blood type. It reads, each child born into a particular set of parents has a probability of 0.25 of having blood type O. If these parents have 5 children, what is the probability that exactly 2 of them have type O blood? The count of children with type O blood is a binomial random variable x with n equal to 5 and probability equal to 0.25. We want to know P of x equal to 2. So please make sure you're looking at the book and seeing the notation that's used there. So we're told this is a binomial setting, so the children inherit blood independently. We're looking at a fixed number of children, 5 children. Each of them has the same probability of success, and each of them fall into 2 categories. You either have type O blood or you do not. We've looked at examples that might seem similar to this, but I want you to scan down to the bottom of that page in step 2, where the example discusses the arrangements of who does and does not have the type O blood, so the successes and failures. We have, 10 different arrangements of which kids could have the type O blood, and so we're going to take a minute to talk about how to count the number of arrangements without having to list them as they did in the example here. Depending on the math class that you've taken previously, you may or may not have heard of this thing called the binomial coefficient or combinations. Oftentimes you learn about combinations when you learn about permutations, so I don't know if that might jog some of your memories. We have 2 different notations that we use to represent binomial coefficients or combinations. So we have this notation here, with the kind of subscripts kind of before and after a capital C, N telling us the number of observations, K telling us the number of successes. We have this notation, it's kind of in matrix form, where N will always be the top number, K will always be the bottom. And actually, I'm just thinking of a third now that I've seen on the AP before. So kind of like the notation that we use for the binomial distribution, the normal distribution, you might have a capital C and then N comma K in parentheses. So 3 different ways to represent this. The formula is given here. So remember that a factorial, the exclamation mark, it multiplies any integer by each integer below it down to 1. So for example, 5 factorial is 5 times 4 times 3 times 2 times 1. You do have a factorial button in your calculator. Then your calculator can also complete this entire thing for you instead of you having to use the formula itself. And I encourage you to do it using your calculator, not using the formula, just so that you're not making lots of mistakes. I just want you to know what the formula is. So your calculator is not just doing magic, it is doing something. So what you'll do in order to type these in your calculator is you'll go to the math button, over to probability. Function 3 will say NCR. What you need to do is type first in whatever the N value is, then go to math probability, choose function 3. Then you'll type in the k value, or your calculator is using R, doesn't matter. Then hit enter and you'll get the correct answer. So we'll practice that in a minute. I want to quickly discuss Pascal's triangle, not because you'll need to use Pascal's triangle on the AP test, but to try to tie some things together from your other math classes you may have learned in terms of how we can calculate these binomial coefficients, where the term comes from, and some of you may prefer to use this method. I don't know. So we know that a binomial has two terms, okay? Bi means two. And the binomial coefficients are produced by taking binomials, raising them to the integer powers starting at 0 and continuing on indefinitely. If we were to expand each of these binomials, we know that anything raised to the 0 power is 1. We know that anything raised to the 1 power is itself. If we were to take the quantity x plus y squared, we would get x squared plus 2xy plus y squared, and so forth and so on. What Pascal's triangle does is just take those coefficients and create a triangle out of them. So I'm reading across here from x plus y to the 0 power, that equals 1. The coefficient of 1 is 1. In this next row, where we have x plus y, the coefficients are 1 and 1. In the next row, x squared plus 2xy plus y squared, the coefficients are 1, 2, and 1. In the next row. And I can construct the coefficients without actually looking at the expansion from here on out. So here's how that works. You have to know that you start with 1 and that the next row is a 1 and a 1. Now, you would get this value of 2 by adding these two values kind of above and diagonal from it together. So this 3 comes from the addition of 1 and 2. The next row, so they always start with 1, would be 1, 4, because that's the addition of 1 and 3, 6, 4, 1. And if we were to go through the tedious process of multiplying x plus y to the 4th power, we would get 1x to the 4th plus 4x to the 3rd y plus 6x squared y squared plus 4xy cubed plus 1 y to the 4th. So the triangle is constructed from the coefficients, or you can construct the expansion from the triangle. So the top row right here is called row 0 because it's produced from an exponent of 0 from our binomial term. Then we have row 1, row 2, row 3, and so forth and so on. Entries are listed the same way. So each of these are entry 0, these ones, and then the next one over is entry 1, entry 2, entry 0, 1, 2, 3. And so forth and so on. So if we want to answer a question like, what is 3 choose 1? Or 3 combination 1, we would go to row 3. So 0, 1, 2, 3. And then go over to the first entry. So this is the 0 entry, this is the first entry. 3 choose 1 is 3. So you can pull these combinations from the table. If we had another example where we wanted 4 choose 2, we would go to the 4th row, over to the 0, 1, 2, so second entry, kind of in that 3rd spot, and that answer would be 6. Let's just do one more example, even though I have 3 spaces here, just to make sure that you can use your calculators to compute these combinations. That is what I want you to be doing on your AP test and on my exams as well. Just, again, trying to tie in that Pascal's triangle for those of you that have seen it before. Let's practice on our calculators just doing like 6, choose 3. So the first thing you're going to do is type a 6 into the home screen of your calculator. Then you're going to press Math, go over to PRB for probability. You should see function 3 as NCR. Press Enter on function 3. Then you'll press a 3 back on the home screen, press Enter, and you should come up with 20. If you can't figure out how to do that, let me know in class and I will show you rather quickly. So let's refocus just for a minute here. The binomial coefficient tells us how many ways we can rearrange our failures and successes. We still need to account for the probabilities for each failure and success in order to figure out the answer to a question like our blood type example. So we know that 0.25 is our probability of success, and so P is 0.25. I want you to recall that we are looking at n children, 5 in this case, so this is a binomial distribution, 5, 2.5. We have 0.75 as our probability of failure. So if you're looking at example 8.5, you're going to see not only the probability of success, but also the probability of failure represented in the calculations. We're going to raise 0.75 to the third power in our calculations because if we succeed twice, we fail 3 times to make our total of 5 children. To refer just back up here quickly, our 0.25 is squared because we want the probability of 2 successes. So if we put it all together, then we have 0.25 to the second power, so a 25% chance of succeeding twice, a 75% chance of failing 3 times, and we want all the rearrangements. So we want the binomial coefficient of 5 trials and 2 successes. If you type 5, choose 2 into your calculator, you will find that that result is 10, and so you can now avoid having to list out the successes and the failures in as they did in step 2 of the example. Putting this all into your calculator, you're going to get your final answer of 0.2637. And just to reiterate, this is the probability that x equals 2 in our binomial distribution of 5, 2.5. So notationally, this is what you need to understand. We want 2 successes of 5 trials with 25% chance of success. These are the calculations. Here is our final answer. And then as always, you would put your answer into a complete sentence. So in conclusion, binomial probabilities can be calculated as such. If we have the binomial distribution with parameters n and p, so n trials and p as the probability of success, the probability that our random variable x equals some value k is equal to n choose k, p to the k power, 1 minus p to the n minus k. The other way this can be represented, not only with the various notations for the combinations, but sometimes you will see q used to represent the complement of p rather than 1 minus p. So this tells us that if we want k successes, we need to take our number of total trials and their arrangement of the k successes within there, the probability of success raised to the number of successes that we want, and then the probability of failure raised to the power of how many failures we want. These two exponents should always add up to n. And that's it.